there, fellow cosmic explorers. Want to unlock the secrets of the universe without, needing a PhD in physics.
Yeah, that sounds pretty good to me.
Well, today we're diving deep into Stephen Hawking's A Brief History of Time to do just that.
Great book.
It is. This book tackles some of the biggest questions out there. Where did the universe come from? How does it work?
And what's its ultimate fate?
Yeah.
Exactly. It's amazing how Hawking, how he managed to make these complex ideas so captivating for a wide audience.
Right. And Hawking had this incredible wit that shines through in his writing.
Oh, yeah. I mean, he outsold Madonna on the bestseller list. Who knew theoretical physics could be such a hit?
Right. Like he once quipped that his book sales rivaled Madonna's overall appeal.
Right. Yeah. I mean, Hawking's book stayed on the London Sunday Times bestseller list for a whopping 237 weeks. That's incredible.
That's amazing. For a book that delves into mind-bending concepts like relativity and quantum mechanics.
Yeah, it's really something else.
So, to kick off our deep dive, let's rewind the clock and trace how our understanding of the universe has evolved over time. It's wild to think we went from believing Earth was the center of everything
Right.
to realizing we're just a tiny speck in this vast, ever-expanding cosmos.
Yeah. What's fascinating is that even early models of the universe, like Ptolemy's Earth-centered view, were surprisingly accurate for their time.
Accurate, but definitely had their quirks. I mean, imagine trying to explain why the moon doesn't always appear twice as big, even though their model suggested it should.
Exactly. That was a major challenge for the Ptolemaic model.
Yeah.
But it held sway for centuries, partly because it fit with the religious beliefs of the time, leaving space for heaven and hell beyond the sphere of fixed stars.
Oh, wow. Then comes Copernicus, shaking things up with his radical idea of a sun-centered system.
Right.
And of course, we can't forget Galileo and his trusty telescope.
Oh, yeah, Galileo.
Yeah.
His observations truly revolutionized our understanding of the cosmos. When he observed Jupiter's moons orbiting that giant planet,
Yeah.
it provided compelling evidence against the Earth-centered view.
Makes sense.
After all, if those moons were circling Jupiter, clearly not everything revolved around Earth.
Right. Talk about a paradigm shift. It must have blown people's minds back then. But as our knowledge expanded, things get, well, a bit more intricate. Now we have two major players in modern physics. General relativity, governing the universe at large scales.
And quantum mechanics, which delves into the incredibly tiny world of atoms and subatomic particles. What's truly intriguing is that these two theories, while incredibly successful in their respective domains, seem to be fundamentally at odds with each other.
Okay, now things are getting really interesting. This inherent conflict between general relativity and quantum mechanics is one of the biggest mysteries physicists are still wrestling with today. So, to really appreciate the brilliance of Hawking's work, we need to unpack these two theories a bit further. But first, let's take a closer look at relativity and how it completely warped our understanding of space and time.
Relativity is where things start to get truly mind-bending. One of the most counterintuitive ideas is that there's no such thing as absolute rest.
Hold on, no absolute rest. So even when I'm just, chilling on the couch, I'm actually still in motion.
Exactly. It all depends on your frame of reference.
Yeah.
Imagine you're on a train, tossing a ball straight up and down.
Okay.
To you, the ball's motion seems simple.
Right.
But to someone standing on the platform, watching the train whiz by, the ball is also moving horizontally along with the train.
So they both see it differently.
Yeah.
So both observers are right.
Precisely. There's no single correct perspective. What matters is the relative motion between the observer and the object. And this seemingly simple concept has some profound implications, especially when you bring in the speed of light.
Okay, speed of light. That's where things went from 0 to 60 for me when I first read A Brief History of Time.
Einstein's big breakthrough was realizing that the speed of light is constant, regardless of how fast the observer is moving. This completely shattered our previous understanding of space and time as separate entities.
So instead, they're interwoven into this fabric called space-time.
That's it. And this space-time fabric can be warped and curved by massive objects, like stars and planets.
Interesting.
Instead of thinking of gravity as a force pulling things together, we can visualize it as the curvature of space-time caused by these massive objects.
So, instead of Earth pulling on me with its gravity, it's more like Earth is creating a dip in space-time and I'm just rolling along in that dip.
That's a great analogy. And this curvature has some really bizarre consequences. Remember the twin paradox Hawking talks about?
Vaguely. It's the one where one twin, like, chills on Earth while the other goes on a high-speed space adventure.
Right. And because of time dilation, the twin who's been zipping around at high speeds actually ages slower than their Earthbound sibling.
Whoa, so if I want to stay young forever, I just need to find a really fast spaceship.
Well, the time difference would be minuscule, unless you were traveling at a significant fraction of the speed of light.
Yeah,
But
right.
it highlights that time is not absolute. It's relative to your motion and the gravitational field you're in.
This is seriously blowing my mind. And what about those light cones Hawking
Yeah.
describes? Those always seemed a bit abstract to me.
Light cones are a way to visualize the limits of causality in space-time. Imagine a cone extending outward from every event in space and time. The cone represents all the possible paths that light could take from that event.
So anything inside the cone is connected to that event?
Yes, events inside your past light cone could have influenced your present moment. And you can only influence events that lie within your future light cone.
Okay.
Because nothing travels faster than light, events outside your light cone are causally disconnected from you.
That means we're always seeing the past, aren't we? Like,
Right.
the light from distant stars has taken millions or even billions of years to reach us.
Absolutely. We're looking back in time whenever we gaze at the night sky. It's as though the universe itself is a giant time machine.
Okay. I need a moment to process all this before we move on to the next mind-blowing topic.
Take your time. These ideas are not easily digested.
I know.
But to continue our exploration of the universe's grand story, let's talk about the Big Bang and the idea of an ever-expanding universe.
All right, on to the Big Bang, where things really get explosive, literally.
It all started with Edwin Hubble's groundbreaking observations in the 1920s. He noticed that galaxies are moving away from each other, and the farther away a galaxy is, the faster it's receding.
So it's like the universe is a giant balloon that's constantly inflating, with galaxies stuck on its surface being carried further and further apart.
That's a perfect analogy. And this expansion implies that if we rewind the clock, everything must have originated from a single, incredibly dense point,
The Big Bang.
the Big Bang.
But what evidence supports this Big Bang theory besides the expansion we observe today?
There's actually quite a lot. One compelling piece is the cosmic microwave background radiation, a faint afterglow of the Big Bang that permeates all of space.
Didn't Hawking mention something about this radiation being discovered by accident? Something about bird droppings?
Oh, yes. Arno Penzias and Robert Wilson were working on a sensitive microwave antenna and kept picking up this persistent noise they couldn't explain. They even tried cleaning bird droppings off the antenna, thinking that was the culprit.
Wait, they thought bird poop was causing cosmic signals. That's hilarious.
It is. But what they eventually realized is that they'd stumbled upon this incredibly important relic of the Big Bang. It was a major confirmation of the theory.
So this noise was actually the faint echo of the early universe.
That's incredible. And what about the abundance of light elements in the universe? I remember that being mentioned in the book as well.
Right. The Big Bang theory predicts that certain light elements, like helium, would have formed in the intense heat and pressure of the early universe. And the observed abundance of these elements matches the predictions remarkably well. Okay, so we have the expanding universe, the cosmic background radiation, and the abundance of light elements all pointing towards the Big Bang. That's a pretty convincing case.
It is. But there are still some profound questions that linger.
Yeah.
What caused the Big Bang? What, if anything, came before it? These are questions that continue to drive cosmological research.
And it makes you wonder, what about the future of the universe? Will it keep expanding forever? Or will it eventually collapse back in on itself?
That's a great question, and it leads us to one of the most fascinating and mysterious objects in the universe. Black holes.
Oh, yes. Black holes, those cosmic enigmas where gravity reigns supreme. Tell me more about those.
Black holes, they're like the ultimate cosmic vacuum cleaners,
Yeah.
sucking up anything that gets too close.
Right.
I remember reading about how they form from the collapse of massive stars.
That's right. When a star much larger than our sun runs out of fuel, it can no longer withstand its own gravity.
Mhm.
It implodes, collapsing in on itself and crushing its core into an infinitely dense point called a singularity. And surrounding this singularity is the event horizon, the point of no return.
Right.
Anything that crosses that boundary is doomed to be pulled into the singularity. Talk about a one-way ticket to oblivion.
It's a pretty dramatic end.
Yeah.
But here's where things get even more intriguing. Hawking made a groundbreaking discovery that black holes aren't completely black after all.
Wait, really? I thought nothing, not even light could escape a black hole.
That's the classical picture. But when you bring in quantum mechanics, things get more complex.
Okay.
Hawking showed that black holes actually emit a faint radiation, now known as Hawking radiation.
So how does that work? If even light can't escape, how can anything be radiated out?
It has to do with those virtual particle pairs we talked about earlier, those particles and antiparticles that constantly pop in and out of existence in the vacuum of space.
Right.
If one of these pairs forms near the event horizon, one particle might fall into the black hole while the other escapes.
Hmm.
The escaping particle becomes real and carries away a tiny bit of energy from the black hole.
So black holes are slowly leaking energy and shrinking over time.
Exactly. It's an incredibly slow process, especially for supermassive black holes.
Mhm.
But it was a revolutionary insight that changed our understanding of these cosmic behemoths.
It's amazing how Hawking combined general relativity and quantum mechanics to make this discovery. Speaking of quantum mechanics, we've only scratched the surface of that bizarre world.
Right.
Didn't Hawking say something like, anyone who is not shocked by quantum theory has not understood it?
He did. Quantum mechanics is full of mind-boggling concepts, like the uncertainty principle, which states that we can never simultaneously know both the position and momentum of a particle with perfect accuracy.
So it's not just a matter of our instruments not being good enough. There's a fundamental limit to what we can know about the subatomic world.
Precisely. It's baked into the fabric of reality. And this has profound implications. For example, the uncertainty principle prevents matter from collapsing in on itself. Instead of having a definite position, particles are more like fuzzy clouds of probability.
So those neat little diagrams of electrons orbiting the nucleus, like planets around a star, are actually misleading.
They are. Electrons don't follow well-defined paths. They exist in a superposition of states smeared out across space.
This is all so weird and wonderful. It's fascinating how these quantum phenomena underpin the behavior of matter at the smallest scales. But how does this connect to the larger questions about the universe that Hawking was trying to answer?
One of the biggest challenges in physics is to reconcile general relativity, which describes gravity and the large-scale structure of the universe, with quantum mechanics, which governs the subatomic realm.
Right.
Finding a theory of everything that unifies these two pillars of modern physics was a driving force behind much of Hawking's work.
So he was searching for a single set of rules that could explain everything from the smallest particles to the largest structures in the cosmos.
Exactly. Hawking explored various approaches, including supergravity and string theory, which both attempt to bridge the gap between general relativity and quantum mechanics.
I remember those names from the book, but they're still a bit hazy for me. Could you give us the deep dive explanation?
Supergravity extends general relativity by introducing additional particles and symmetries. It's a beautiful theory mathematically, but hasn't yet been experimentally verified.
And string theory, that one always sounded pretty out there.
String theory is even more radical. It proposes that the fundamental building blocks of the universe aren't point-like particles, but tiny vibrating strings.
Okay.
And it suggests the existence of extra spatial dimensions curled up so small that we don't perceive them directly.
Extra dimensions. So like our universe is just one slice of a much larger multidimensional reality.
That's the idea. It's a mind-bending concept, but string theory offers a potential path towards a truly unified description of the universe.
This is all so incredible. But amidst all these mind-blowing theories and discoveries, I keep coming back to this one question. Why does time seem to move only in one direction?
Ah, the arrow of time. That's one of the deepest mysteries in physics.
Hawking explored various aspects of this question.
Discussing the thermodynamic arrow of time related to entropy, always increasing the psychological arrow of time tied to our perception of past, present, and future, and the cosmological arrow of time linked to the expansion of the universe.
So there are multiple arrows of time.
Right.
It's like all these arrows are pointing in the same direction towards the future. But why?
That's the million-dollar question Hawking proposed, that the universe's initial conditions at the Big Bang, along with his no-boundary proposal, which suggests the universe is finite but has no edges in imaginary time, could explain this alignment of the arrows of time.
Okay. That's a lot to unpack. But it sounded like Hawking was trying to connect the origin of the universe to the very nature of time itself.
He was, and his work pushed the boundaries of our understanding of these fundamental concepts. But even with all these advances, there are still so many unanswered questions.
Which is what makes cosmology so exciting. There's always more to discover and explore.
Exactly. As we delve deeper into the mysteries of the universe, we not only learn about the cosmos, but also gain a deeper appreciation of our own place in this vast and awe-inspiring tapestry of existence.
Well said. I think we've covered a lot of ground today. From the evolution of our understanding of the universe to the mind-bending concepts of relativity, black holes, and quantum mechanics, it's been a wild ride through a brief history of time.
It has. And I hope our deep dive has inspired you to continue exploring these fascinating ideas.
Definitely. And remember, as Hawking said, look up at the stars and not down at your feet. Try to make sense of what you see and wonder about what makes the universe exist. Be curious.
And keep in mind Hawking's thought-provoking words. The greatest enemy of knowledge is not ignorance, it is the illusion of knowledge. Always question, always remain open to new ideas, and never stop exploring the wonders of the universe.
That's a perfect note to end on. Thanks for joining us on this deep dive into Stephen Hawking's A Brief History of Time. Until next time, keep looking up, keep questioning, and keep diving deep into the mysteries of the cosmos.